Okay, good morning. The title of my talk is Mechanical Control of Photochemical Processes, Computational Strategies and Tools. And I want to present some tools that are currently available on OpenMOLCAS to apply mechanical forces to molecular systems, and especially for the study of photoinduced processes, photochemical reactivity, and photophysical properties. Okay, the outline of my talk is the following. I will do a brief introduction on mechanochemistry, especially when the forces are applied in photochemical systems that can undergo some photochemical reactivity, or in the case that we are studying some photophysical property. Then I will explain the current implementations in OpenMOLCAS to perform these calculations, these simulations, and finally I will talk about the future implementations that we plan to implement in OpenMOLCAS. So it's possible to apply mechanical forces to molecular systems experimentally. Here are a few examples, the most common ways to introduce these forces. For instance, we can use AFM. In this case, in this example, we have two reactants, two molecules that can undergo a chemical reaction, in this case a Diels-Alder reaction. So applying a specific force on these two molecules, it's possible to induce the chemical reactivity of the system in a, let's say, controlled way. It's also possible to use force proofs. This is a quite common way to introduce mechanical forces. So in this case, we have a molecule which is called mechanophore that can undergo some chemical reactivity. And if we attach to this molecule a molecular system that introduces some strain to the system, in this case, this strain is controlled because this force proof is in fact a photo switch that has two states, cis and trans. So in the trans isomer, the force, the applied force or the induced force is large. In the cis isomer is not so large. So the application of this force through the force proof can, in this case, for instance, to affect the chemical reactivity, in this case, the kinetics of the system. Sonication is also another way to apply experimentally this force. In this case, we have two polymers. Again, we have the mechanophore, the molecule that can undergo a chemical reaction. And if we attach some polymer chain in solution when applying ultrasounds, so using sonication, these polymers are moving, and this movement is transmitted to the reactant molecule and can affect mechanically also its reactivity. And finally, another usual way to introduce the forces on these systems is using polymer mechanochemistry. In this case, the mechanophore is embedded in the polymer chain, and if we apply some macroscopic force, it's possible to induce a chemical reaction. In this case, the spiropyran, when applying a force, can induce the breaking of this bond. So in this case, the color of the system is changing because of the conjugation of the system. Okay, this is the most usual ways to introduce these forces experimentally. There are also, let's say, classical mechanochemistry, which is just applying mechanical force using for instance, ball milling technique. In this case, these balls inside the reactor heat the reactants, usually in the solid state, and may induce a chemical reaction. This experimental setup is available on the lab scale, but also it's commonly used in industry. Okay, so to understand the effect of these mechanical forces, let's consider a potential energy surface, a simple potential energy surfaces. Here we have the ground state potential energy surface. There is a minimum, a transition state. So let's consider the variation in the activation energy due to a mechanical force. So if we have no force, we have an activation energy. But if we apply a mechanical force, in general, the structure of the minimum and transition state, the structure of every stationary point is changing. Obviously, if we apply a force, we distort the molecule, the system, and this distortion could be small, but in any case, there is a change in the structure of the minimum, transition state, etc. So this displacement of the stationary points make the activation energy to be affected. But also we need to consider the work performed by the applied force along the reaction path. So in this case, if we are considering the movement of the molecule from the minimum to the transition state, we need also to compute, to know the work performed by the force along this path. So it's this term here. So the final activation energy is being affected not only because of the geometry of the change in the geometry of the stationary points, but also because of the work performed by the external force, by the mechanical force applied to the system. And this term usually is the most important one. Here in the 1D example, it's easy to see how the topology is changing, the topology of this potential energy curve. So we have with zero force in green, we have the potential energy. So we have two minimum, we have a transition state, and if we apply a mechanical force, this curve is changing. In fact, we can see that the stability of the minima is the opposite as that we have in green. So now this minimum is lower in energy than this one, and also the transition state energy, in this case the activation energy, is also changing. In this animation, we see a similar situation. So we have applied a force with an increase in magnitude. So we can see that the minima are changing. The structure of the minima is changing. Also, the transition state is displacing with the applying force. And also the relative stability of each point. So in general, applying a mechanical force can affect the reaction energy and the activation energy on the ground state. Okay, in the excited state, I mean, if we are considering different excited electronic states, in this case we have a simple S0 S1 system with a conical intersection. So as you know, if we have no forces, so the system can undergo the activation through a conical intersection, populating the ground state. In this case, we have a chemical reaction because a photochemical reaction because we go from this minimum to this minimum through a conical intersection. So it can be proved that application of mechanical forces can affect also the conical intersection topography. So in this example, we have a conical intersection with zero force. And if we apply an external force with a given component along the branching plane, it's possible to show that the tilt of the conical intersection is being affected. So here we have an animation in this sense. So as the component of the force along the branching plane is increasing, the tilt of the conical intersection is also changing. Okay, now I will show some examples of mechanical control on photochemical processes with what we call mechano-photochemistry. So these examples are computational examples, so they are systems that we have studied using these tools. So the first case is the benzene molecule. Benzene molecules have given photoreactivity. The reactivity goes through the S1 state. So we studied this system where we are applying a mechanical force, a force pair in this case, on two methyl groups that we attach to these two carbon atoms. And it's possible to show that if we apply a force that is around 1 nanonewton, the slope of the conical intersection is affected. It goes from peak conical intersection for 0 nanonewton to a slope conical intersection for 1 nanonewton. Here are the S0 and S1 surfaces for this system, and we can see that not only the topology of the topography of the conical intersection is affected, but also there is a minimum for force equals 0 that is disappearing as we apply the force. So we go from this situation with 0 force, this situation which is related with the photoreactivity of the system, to this tilt, this slope conical intersection, which is related with photostability. In the case of a steel beam, we made an experimental and theoretical study. In this case, the forces are applied using force proofs. So we have this system, the steel beam molecule, and we attach to this system different chains of different length with different CH2 units. So using different length, we can modulate the applied force. In case of no forces, which is the surface in green, we have a given, this is the S1 state, so this is the excited state. We have a minimum on the excited state, and we have a transition state, so we have an activation energy. This system, if it's able to overcome this transition state, undergoes the photoisomerization. So as we apply a force, an increasing force, the topology of the potential surface is changing from 1 to 2 to 3. And it's apparent that the transition state is becoming closer to the minimum on the excited state, and the activation energy is also decreasing. So we can see also experimentally that as the applied force increases, the quantum yield of fluorescence is decreasing and the photoisomerization is increasing. Of course, if the quantum yield of fluorescence is decreasing, this is because it's also affected the lifetime of the excited state. which is larger in this case in the zero force situation, and is decreasing for increasing forces. Also, the triplet excitation energy can be affected. These are different examples. So in this case, we are studying this oxide IP methane molecule that can undergo triplet energy transfer. So the triplet energy, which is possible for the system to accept, given a donor molecule. So this energy can also be affected. We can see here the effect on the applied force. So for CO force is around 80 kilocal per mole. So as the applied force, this specific force pair is increasing, so up to 1 nanonewton. This triplet energy is also increasing, and then it goes more or less unaffected for 1 to 2 nanonewtons. Okay, this is the result of different conformations weighted by its population, but the idea is that this triplet energy can also be affected due to the applied force. So one central question in the study of all these processes is to understand how a given mechanical force can modulate the energy difference between two electronic states, or in a general way, what's the optimal way to control, to modify this energy difference. So in this case, we have a ground state, we have an excited state, and this is map. The color corresponds to the force. So to the force in the sense that if we apply a given force and the minimum is displaced to this point, all these points, for instance, in this ellipse, they have the same force magnitude. So all these points correspond to the same force magnitude. So again, we have the same situation. All these points correspond to the same applied force magnitude. So we are interested under the restraint of a constant force magnitude, of applied force magnitude. We're interested in the points that corresponds to the largest variation on the excitation energy, or in general the energy difference between these two states. That could be this one and this one. This decreases the energy difference, and this is the largest variation increase in the energy difference. So to do that is quite easy. We construct this Lagrangian function, which is this is basically the force magnitude, and this is the restraint. So the energy difference is constant. The energy difference between the two states is constant. So solving this optimization process, so it's possible to obtain the optimal geometry, so the optimal displacement of the molecule from the minimum, which is related with the Hessians. These are H matrices are Hessians on the initial state, H0, and the excited state, H1, and also the gradient of the excited state for the minimum energy point. Also, it's possible not only to obtain the optimal geometry, but also the optimal forces doing this computation. So here is an example, a very simple example. This is the retinal chromophore. So if we are interested in knowing what's coordinates are the most efficient in changing in this case, the singlet triplet energy difference, we can apply this procedure, and by solving the equations, the system of equations, we can obtain the most relevant coordinates, in this case these two torsions for decreasing this singlet triplet energy, and this torsion for increasing this energy. Okay, so currently there are few tools for studying these systems or these procedures, including external forces on OpenMOLCAS. So basically, we have a module that can define some external force in the system, and the most common way to use it is by performing non-adiabatic molecular dynamics. So this module is EXTF, external forces. So in the current implementation, we have the possibility of applying a force pair. Given two atoms, we can apply a force pair, which is basically two forces along the line connecting the two atoms, in this case 1 and 2, and it can be used, as I said, to perform non-adiabatic molecular dynamics with the module surface hub, which is included in the dynamics or is working within dynamics module developed by Igor Sapiro. And both are available, both modules are available on OpenMOLCAS and MOLCAS 8. With these modules, specifically with the AXTF module, we can perform minimum energy path with explicit application of mechanical force, like in this case, where we are studying a photocycle addition, 2+2 photocycle addition. So here we have different minimum energy path with 0 force, 1 nanonewton force, and 2 nanonewtons. So the minimum energy paths are different. In this case, they go to a conical intersection, but in this case, for large forces, it reaches a minimum on S1. It's also possible, as I said, to perform non-adiabatic molecular dynamics. Here is an example of an input to do this. And let's say if it's possible. No. Sorry. Okay. Okay, so this is a trajectory computed with these two modules, EXTF and surface hub. When we apply a force pair here in these 2 points, these are 2 methyl groups attached to this minimum retinal chromophore. It's a model chromophore. So we can study in this case, the cis to trans, the trans to cis photoisomerization. Okay, so the idea is to implement a few additional utilities in the EXTF module. So the first question is to be able to define different external forces, not only force pairs, but forces involving angles between 3 atoms, torsions and improper torsions. So dihedral and improper torsions. We would like also to provide more flexibility to the external forces applied. is being able to specify in a molecular dynamic simulation when the forces are applied and some conditions related to these forces. We also would like to add a force field to specific coordinates. So in this case, if we want to substitute a given, for instance, let's consider these two atoms that are linked. So the idea is to be able to replace the internal force by a given force defined by the user. So in this case, we are maybe mimicking situations that cannot be exactly reproduced or simulated using force pair. And also an important thing is to track the work developed by the applied force in given coordinates. So this can provide us important information on the work that is applied to the system and how this work is affecting the photoreactivity of the system. We will also would like to implement, as I said, the optimal mechanical response in a first order. So these two equations. So the idea is to be enabled from Hessians and gradients to get a first approach in the optimal force controlling a given energy gap between two states. And also to introduce the possibility of doing force pair analysis, which is basically to identify which force pair is more efficient in modulating a given energy difference between two states. Okay, so in summary, I think that the implementation of mechanical forces can provide new possibilities in the control of photochemical process and photophysical properties of systems. Current implementations in OpenMOLCAS are the application of force pairs. We can do minimum energy paths or perform semi-classical molecular dynamics, non-adiabatic molecular dynamics, including Boltzmann sampling. And the new implementations that we are planning to introduce are the extension to other type of mechanical forces in general, to be enabled to obtain the first order mechanical response in the energy gap, the variation of the energy between two states, to being able to do an analysis of force pairs for a molecular system, and to obtain also information about the work developed by this applied force. Okay, so finally, I would like to thank to the Ministry of Science and Innovation of Spain for the supporting and the University of Alcalá. Thank you very much.